Hall effect is an interesting microscopic effect due to the motion of the charge carriers, and it was very important for determining that the charge carriers were in fact electrons, or negative rather than positive charged particles. And again, it was discovered in 1879 by its namesake, Edwin Hall. And again, he developed a setup to measure the amount of force that is placed on this moving charge due to an external magnetic field. And again, this experiment allowed the size and sign of the charge carriers to be determined in a conductor, and it led to the realization that metals use electrons to carry current. So very, very important. Here's basically the setup. We can imagine that we have a magnetic field going in this direction right here. The current is traveling this way. So if we think about V cross B, the force on positive charge carriers is going to be in this particular direction. Now the reason why the Hall effect could actually determine the direction of the charge carriers is because if we imagine it this way, let's say that we had positive charge carriers traveling with the current in this direction. Again, our magnetic field is going in this direction right here. We have V cross B. There is going to be a net force downward on the charge as it's moving in that particular direction. But for the same current going in that direction, if the charge carriers are negative, we actually have the opposite of the right-hand rule. Here we have V cross B, and now the electrons are feeling a downward force. Look at the difference between these two. Here, the positive charge was on the bottom, the negative charge was on top, for a current going from right to left. For the same current going from right to left with a negative charge carrier, we ended up with a negative potential on the bottom and a positive potential on the top. Very simple experimental setup, but what was so amazing about it is it told you exactly what the sign was. And given the charge of the carrier, it also gave us an idea of what the potential should be, or I should say, given the potential set up by this by Hall's experiment, you could also tell what the charge of the electron was. So again, looking at this and analyzing everything that's going on right here, the voltage in one of these Hall setups is equal to how much current is going through, the strength of the magnetic field, the length of the conductor that we're using, the charge density of the charge carriers, the charge of the charge carriers, and the cross-sectional area. So current, magnetic field length, cross-sectional area could all be measured. And again, from this you could get the charge of the carrier, charge of the charge carriers, and their charge density for a particular metal. And again, this would be equal to the magnetic field times the length times the drift velocity.